Hi folks, I am not even going to introduce myself. That's so counterintuitive. Ha 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 ha. Let's just get straight to the topic. In this video we will construct polynomials that satisfy some special properties, namely that they give specific outputs at specific inputs, which is just another way of saying that they pass through certain points on their graph. Let's begin. Imagine that we want a polynomial p of x such that the following properties hold. These properties are equivalent to saying that the graph of p of x must pass through 2 points listed in the transcript below. First, we will start by constructing p of x such that only the highlighted property holds. Here, we have constructed the polynomial. We can verify that the highlighted property holds by just inserting x sub 1. Now, let's say that we want to satisfy the remaining property. We can modify our current polynomial to achieve this. We know that this is the value of our polynomial at x sub 0, but we want it to be 1. So, let's divide our polynomial by x sub 0 minus x sub 1. Now, we have successfully created a polynomial that satisfies both of the highlighted properties. Let's demonstrate our polynomial by setting x sub 0 equal to 1 and x sub 1 equal to 2. If we graph this polynomial, this is what we get. Our polynomial is 0 at x equals 2 and 1 at x equals 1, which is what we wanted. So, indeed our polynomial does work. But, what would our polynomial be if we want the above highlighted properties to be true? Or what should p of x be such that its graph passes through the points listed in the transcript? Just like before, let's modify our polynomial so that one of the properties is satisfied. Notice that p of x sub 0 equals 1, but we want it to equal c sub 1, so we just multiply our polynomial by c sub 1. Now, let's modify our polynomial such that the other property is satisfied. Notice that p of x sub 1 equals 0, but we want it to be c sub 2, so let's just add c sub 2 to our polynomial. But, this polynomial has a problem at x sub 0, it doesn't equal c sub 1. We can actually fix this by making the second term of the polynomial disappear at x sub 0, and be equal to c sub 1 at x sub 1. It is left as an exercise for the viewer to show that the following term corrects our problem and also show that our polynomial now satisfies both properties. Now, let's construct a polynomial with the following properties to verify our technique. So, here's the graph and our polynomial indeed satisfies both properties. So far, we have found this way of constructing a polynomial such that it satisfies the highlighted properties. But, what if we want to satisfy these three properties instead? We will have to modify our polynomial again. Now, we wouldn't like the first and the second terms to interfere with the value of the function at x sub 2, so let's modify them such that they equal 0 at x sub 2. Now, as both of the terms disappear at x sub 2, therefore we can add c sub 2 to our polynomial. Now, this does give us the correct value at x sub 2, but interferes with the values at x sub 0 and x sub 1. We can correct this by modifying the third term such that it is 0 at x sub 0 and x sub 1 and c sub 2 at x sub 2. Now, it's left as an exercise for the viewer to verify that this modification allows the polynomial to satisfy all of the highlighted conditions. Now, let's construct a polynomial satisfying the following. As you can see, our polynomial does satisfy the conditions shown on the upper right corner. We were quite successful in constructing polynomials that pass through 2 or 3 points. But, what if we want a polynomial passing through 12 or even 100 points? Wouldn't it be really nice if we had a formula that gives us that polynomial? This is exactly what we are about to show. Actually, our expression for n equals 3 case was of this form. It can also be written as here q sub j of x satisfy a special property. They are 0 at every other point except x sub j where they are 1. And for n equals 2, we have this. Now, it would be tempting to say that this is the formula for arbitrary n. And you would be correct. But, we should verify this. This is the expanded form of the sum. We will keep in mind the special property of q sub j of x. They are 0 at every other point except x sub j where they are 1. And evaluate p of x at every relevant point. So, it does work. Now, it's time to find q sub j of x. We will need this special property of q sub j of x. They are 0 at every other relevant point except x sub j where they are 1. So, here's the expression for q sub j of x. The numerator must not contain x minus x sub j and denominator x sub j minus x sub j. Because if it does, then q sub j of x will violate its own property. So, p of x is